Hello everyone. In this problem we have a direct current circuit with 3 resistors shown on the left, and then a chart on the right with some filled in information and some other unknowns, and your job is to look at the circuit and take what you're given and figure out all the rest and fill in the boxes. And then there's some follow-up questions here. And you can see there's some scenario, some kind of long-winded real-life example here, some global problem-solving scenario down here. It doesn't really matter, but the point is you've got this circuit about which some things are known and other things are not known. So let's go ahead and see what we can figure out. This is a rather easy problem. You just have to look at the table over here and determine what you can do using Ohm's law. It's pretty much the only relationship I'm going to use for a while here. Delta V equals IR. So let's see, where should we begin? It looks like for resistor A, right here, that's this guy, I know 2 of these things, the voltage and the resistance, so that means I should be able to calculate everything else. So the current through resistor A would be using the 50 volts and the 5 ohms and simply dividing according to this. I would come to the conclusion that the current was 10 amps. And I think to help, let's put an arrow in the diagram showing the flow of that current, and let's label it 10. Oops, come on now. 10. Yeah. Let's try that again. $10 There we go. All right. Now that current's going to split when it hits this junction right here. Some of it's going to go to the left, and some of it's going to go to the right. How much goes which way? Well, I'm told that the current in resistor B is 6 amps. That's great. So if this is 6, then I immediately know that this is 4. Okay? According to the fact that charge is conserved at that point right there. Okay, what does that tell me? Well, knowing that resistor C has 4 amps will probably allow me to calculate the potential difference across resistor C. Again, using Ohm's law, with 4 amps and 8 ohms, I come to the conclusion that the voltage across the resistor is 32. Right? But wait a minute, that means that the voltage across resistor B is also 32, because resistances in parallel must have the same voltage drops across them. In fact, any circuit elements in parallel must have the same voltage drop across them. So while I'm at it, I might as well take a moment to just say something like, if you had a capacitor in a circuit and also a resistor, and they happened to be in parallel with each other, like so, and this is just part of a circuit, I'm not going to draw the rest of it, right? Then whatever voltage drop exists across the resistor at any moment in time must be identical to the voltage drop that exists across the capacitor at that same moment in time. Right? That is a fundamental rule. It comes back to what we're going to define as Kirchhoff's loop rule. That's really the reason for that. But we'll see that in a day or so. Okay, so that being said, I think the only thing left, well, I have to calculate the resistance of resistor B, and that's easy. It's just 32 volts divided by 6 amps, and that turns out to be, I think, 5.33. All right, giving you the illusion that I just did that in my head. I could have a calculator, you have no idea. You can't see me. And finally, the battery. The battery would be, let's see, for voltages, it's got to be 82 volts. And why? Well, because around any path that I might take, if I take this path right there, around like that. Any voltage that I gain going across the battery must be equal to the sum of all the voltage drops along the way. And since I'm going to lose 50 volts across resistor A followed by 32 volts across resistor B, that's a total loss of 82 volts. That means I must pick up 82 volts at the battery, crossing the battery. And the same would be true if I took the other loop. In other words, if I went and I happened to go that, if I were a charge that happened to follow that outer path, it would be the same thing. Okay, so 82 volt battery telling me the current is, well, I already know the current in the battery is 10 amps because that's the current in resistor A, so that's been known since the beginning. I just didn't bother to fill it in, like so. And now to calculate the power, I simply multiply current times voltage in each case. So this here comes out to 10 times 82 is 820 watts, right? 50 times 10 is 500 watts. 32 times 6 is, let's see, 6 times 30 is 180, and 6 times 2 is 12, so 192 watts. And resistor C is 4 times 32, 128 watts. And what I better see, if I add these all up, 128, yes, is that the bottom three need to equal the top. That's the law of conservation of energy right there, which I've mentioned in previous videos. 500 watts plus 192 plus 128 adds to 820. Of course it does, right? So the power input to the circuit by the battery must equal the power output, which is the sum of all those resistors. Okay. Now the questions. How much total charge in coulombs passes through the battery during the time that the circuit was connected? Well, the definition of current would help us here. The definition of current is I dq dt, the rate of change of charge with time. And I want the total charge. I want Q. So we're going to take that and rewrite that as its inverse operation, which is an integral, an antiderivative, right? So the total charge will be the antiderivative of I, assuming that I is a function of time, so I of t, with respect to time. Now this comes in handy if you actually have a current that's time varying. If you had a function, I of t, so say, for example, this is just an example, it probably doesn't pertain here, but say that you knew that I was equal to some initial current, or some maximum current rather, times the sine of omega t, where omega is some angular frequency, so you have a sinusoidally varying current as you have with electricity in your homes. That would be an alternating scenario, where, by the way, the frequency is 60 oscillations per second. So if you had such a current scenario, you could plug that in and determine over a period of time what total charge had transferred. What's interesting is that if you do that in a scenario like this with a function such as this, if you choose an entire period, if the period matches the, in other words, if the period of time you're integrating over is the period of the oscillation itself, what you'll find is the net charge transfer over that period of time is actually zero. And that kind of makes sense if you think about charges going back and forth, back and forth, back and forth. They don't, in an alternating situation, they don't really go anywhere over the long haul. Well, we don't have that scenario in this problem. I thought it was just an opportunity to talk about that. But in this problem, we just have just a uniform current that's constant in time, and that current in the battery is 10 amps. So we can dispense with the integral and simply say that the total charge Q, I'll write up here because I'm running out of room, so the total charge Q is just equal to the current times the time times delta T. All right, in other words, an amp, which is a coulomb per second, times a certain number of seconds, will end up giving me a coulomb if we just do it with a unit analysis. So easy enough. I've got 10 amps. And how long was the circuit connected for? I don't think I know that because I kind of clipped off my important information that was down here in the diagram, but I think I happen to have it somewhere else, even though you can't see it. And what does it say? It says, so I might be missing it somewhere. Maybe you don't know. Yeah. Okay, so you know what? It doesn't really matter. Because that's the answer. It's simply the current times the time. All right, done. So, moving on. If the students who built the circuit connected an additional wire with no resistance between points E and F, explain what would happen. So, let's see, points E and F are here, down here, where I'm coloring, and here. So let's connect a wire like so. Question is, what would happen? And why? And the answer is absolutely nothing, given a circuit with perfect wires. If there's no resistance whatsoever in these wires, then there's already no resistance between point E and point F. It's this path. So putting another resistance-free path between those 2 points does nothing. Nothing changes. Now, if the wires themselves have resistance, and you connect between these 2 points, E and F, then you've actually provided a parallel path to this one. So if this resistance along the longer path that I'm highlighting right now is some small number, then putting another small resistance in parallel with it will actually cause the total resistance from between E and F to go down, right? Because you provided an alternate route. If that's the case, then the total resistance of the circuit itself will go down. That means that the total current will increase. So instead of having 10 amps in the circuit, we might end up with 10.05 amps. And the net result of that would be to cause greater voltage, or change the voltage drops and the currents through the resistors, which ultimately would end up, if these were light bulbs, making them brighter. Now that would be a relatively insignificant effect because the resistance of wires is small. It's minute, vanishingly small for little tiny short wires made of copper for the most part. So what is the right answer to this question? I think it depends on whether or not you're considering the resistance of the wires or not. Okay. In general, in an introductory physics course, we would answer, well, no, nothing happens because I've just put a second resistance-free path between points E and F. There was already one. In an AP Physics C class, I think a more proper answer is to say it depends. It depends on if the wires are resistance-free or not, as per my last explanation. Okay, and let me erase that. Now, let's get rid of all this markup. And so for the last question, I'm going to connect a wire, this time between D and F, like so. So what would happen now? And the answer is, even in a circuit with resistance-free wires, lots of things will change. Right? Everything changes. Because what I've done now is I've completely bypassed resistors B and C. If I'm a charge traveling, and again, conventional current, so positive charge traveling this way around the circuit, when I hit this point right here, I have a free ride right back to the battery. So from this point on, what I have here is basically just a circuit with a single resistor, and that's RA. No current will choose to take this path through resistor B or this path through resistor C when there's a resistance-free path to get from D to F. All right, and I hope that's clear. You have effectively removed these two from the circuit by shorting them out, by providing an alternate path around them with zero resistance. That really does mean that there will be no current in either resistor B or resistor C. There will be no voltage drop across B or C, because there's no voltage drop across from D to F, because there's no resistance between D and F. So that will have dramatic effects on the circuit. If these were light bulbs, then all the resistors, then B and C would immediately go out. They would go dark, and resistor A would get brighter, right? Because it doesn't have these resistors also in the circuit anymore. Now, all of that is a little bit different if wires have resistance, because if there is some small amount of resistance between D and F, then most of the current will follow that path, but a trickle will still go through B and C. So again, exactly how you answer depends upon whether you're considering wire resistance or not. All right, and there you have it.